Let's see what happens when a new edge comes in. Let's say the new edge is between vertices u and v. There are two possibilities here. The first possibility is that u and v already belong to the same connected component. Right? The sequence of edges that came in before we saw this edge from between u and v, the previous edges were sufficient to connect u and v together in the same connected component. So this new edge u comma v does not affect the number of connected components. It still remains the same as it was before. If, on the other hand, u and v belong to different connected components, then by adding this new edge between them, the number of connected components decreases by 1, because the component to which u belonged now gets unified with the component to which v belongs, and so the total number of connected components decreases by 1. So it seems like an overkill to use the outer loop to run BFS or DFS over the entire graph when the most that can change is that two separate connected components now get unified together into a single component, reducing the number of connected components by 1. If we could somehow keep track of this change in a more efficient way, instead of having to run BFS or DFS over the entire graph, that would potentially speed up our time complexity. Now, since we will need to check which components u and v belong to in order to decide whether it's the same component or not, it might help to associate with each vertex the ID of the connected component to which it belongs. We can track which component each vertex belongs to by giving each connected component a unique ID, and each vertex then would be mapped to its corresponding component ID. Now, this sort of information, which is stored on a per vertex basis, is commonly implemented by creating a separate array, a one-dimensional array of size n, to store that information kind of like an attribute for each vertex. So we've done this with the visited array in BFS and DFS, and you might recall from the live class that we added more arrays. There was a parent array that we added at some point. We added a distance array or a color array, or depending on what kind of problem we were looking at, if we needed additional information to be maintained with each vertex, we would add an additional array. So let's think of adding a component ID array associated with each vertex, which tells us what is the connected component ID to which that vertex belongs. Now, initially, every vertex is an isolate. Since we have not seen any edge yet, every vertex from 0 to n minus 1 is in its own connected components. So why don't we give the connected component an ID which corresponds to the vertex ID itself. So initially every vertex starts out in its own connected component, and so if we have two arbitrary vertices u and v, their connected component IDs would be u and v respectively. Now when the edge u comma v is added, we can just look up directly in this component ID array what connected components they lie in. If those two values are the same, that means they already belong to the same connected component, and so our running tally of how many connected components there are will be unaffected. But if it so happens that these two numbers are not the same, in that case we need to unify those two connected components together, which means that we have to do some operations which will change the ID of either which will change the component ID of v to either u, or change the component ID of u to v. So one of the two must happen. For now, let's assume that we will make that choice arbitrarily, whether to change the component ID of u to v or whether to change the component ID of v to u. Let's say we change the component ID of v to u. So we do that and we decrement the number of connected components by saying something like components minus minus whenever we find that u and v, the endpoints of a new edge, don't share the same component ID. We force them to share the same ID, and then we say that we have one less connected component. Is that going to suffice? Well, not exactly. Suppose that just before the edge u comma v came in, vertex u belonged to a connected component with 3 vertices as shown, and vertex v belonged to a connected component with 5 vertices as shown. Now this new edge which came in between u and v effectively unifies these two connected components. So just changing the component ID of v to be u is not going to suffice, because there are 4 other vertices in the same component as v, and we also need to go and change their IDs. Only then would all of the vertices in this unified component have the same component ID of u. So how do we change the ID of every vertex in the component of v to u? Well, we have to run a for loop which goes something like this. For each vertex, we'll have to iterate over each vertex in the range from 0 to n minus 1, basically look at every possible vertex ID, and we have to check if the component ID of the current vertex we are looking at is equal to the component ID of v or not. Right, let's say v had a component ID of some number. I mean, it could be v itself, or it need not be the same as v, because if all 5 of these vertices share the same ID, then it's going to be one of their IDs, and we don't know which vertex is the leader or the representative of that connected component. But whatever it is, we have to change the ID of all the vertices in this component to u. So we have to check if the component ID of the vertex is the same as the component ID of v, then we have to change the component ID of that vertex to be now equal to the component ID of u, whatever the component ID of u is. So basically we have to go over every vertex, and if we find that the vertex we are at belongs to the component of v, then we have to change its ID to u. Now there is a small bug in this code which you can notice if you pretend doing the following. Let's say we first look at vertex v in this for loop, and we change its ID to whatever the component ID of vertex u was. Now when we look at the next vertex in this same component, is its component ID equal to the component ID of v? Well, no, because the vertex v has already changed its component ID. So this equality condition will be false, which should not be the case, because we really want to treat these 5 vertices as belonging to the same component. So what we should do is we should store the component ID of v, setting it aside in another variable, and then use that variable as the reference ID to identify which vertices belong to the component of v. So we set aside the component ID of v into this variable called old ID, and then we iterate over each vertex, checking if its component ID is equal to that old ID. We would update the component ID to basically be the component ID of vertex u. And why do we have to go through each vertex? Well, because we don't know which other vertices belong to the same component as v. There is no way for us to find that out except by going through and checking every vertex, checking the component ID of every vertex. So this is what we are doing when each edge u comma v is seen. So for each new edge u comma v that comes in, we check if the two endpoints u and v share the same component ID or not. If they don't share the same component ID, then we have to either change the component ID of V and all the other vertices in its component, or we change the component ID of U and all the other vertices in its component. For now, I'm just going to assume that we are breaking the tie arbitrarily and always, let's say we just decide to change the component ID of the vertex on the right. So we basically set aside its component ID value, the component ID value of vertex V, into this old ID, and we iterate over each vertex. If we find that it belongs to the same component as vertex V, we update its ID to be the component ID of U. So you can think of what's going on here as similar to a religious conversion. So basically you have these two groups corresponding to these two different components which are sort of following a different religion given by their component ID, and somehow there are these two people, U and V. They now meet, and maybe U convinces V to change his or her religion, and when that happens, the family to which V belongs also changes. Every member in the family change their religion to now adopt the ID of the new religion. So this operation, which unifies two different connected components together, is called a union operation. It unifies two separate connected components. Now we don't do this union operation for every edge. We first find what component vertex U belongs to and what component vertex V belongs to. So finding out what components they belong to is called the find operation, and only if they don't belong to the same component, only if we find that their component IDs are not the same, do we do the union operation. So what is the maximum number of union operations that can happen in this process? Well, initially the number of connected components is n, and every time a union operation happens, that number decreases by 1. So if there were n separate connected components at the beginning, at the end this number can reduce all the way down to 1. It can't go down further, because at the end all vertices can get unified into a single connected component. So the maximum number of union operations therefore would be n minus 1. Starting from n, how many times can we decrement the number of connected components to reach 1? Well, that's n minus 1. What is the maximum number of find operations? Well, if we follow this process for every edge that comes in, assuming that there are m edges that are going to come in total, basically create, making up the final graph. For each edge that came in, we have to find what components the two endpoints belong to. So we have to do this find operation 2m times, right? 2 times for each edge that came in, once for each endpoint of that edge. Now, what is the complexity of an individual union or find operation? Well, the complexity of a find operation is trivial. We just look up this component ID array, and whatever number is sitting there, that's the ID of the component of U or V. So that's just going to take a constant amount of time. So the total cost of these find operations in the whole process would be the number of find operations times the complexity of a find operation, and that's order m. What about the complexity of a union operation? Well, that is a little more complicated, because when a union operation is done, it's possible that taking that same analogy of religious conversion, it's possible that there could be a large number of members in this connected component, and all their IDs have to be changed. So you can imagine that when this process starts, let's say vertex 0 and 1 get unified, and 1 changes its ID to the ID of 0. Then vertex 2 then there is an edge between vertex 2 and vertex 0 that comes in, and again let's assume that vertex 2 manages to convince vertex 0 to change its ID, and so the ID of not just vertex 0 but also vertex 1 has to be changed. And then when vertex 3 comes in, let's say 3 has an edge to 2, and 3 convinces 2 to change its religion, and so you have to change the component IDs of all three vertices 0, 1 and 2 to basically 3. And so this process could continue until when vertex n-1 comes in. Vertex n-1 let's say has an edge to one of the vertices in the existing connected component, and let's say all the vertices from 0 to n-2 are connected together, and then when this new edge is seen between n-1 and one of the other vertices, let's say vertex n-1 convinces the other vertex to change its ID, and so everyone here has to change their ID. And so you can see here that the maximum cost of an individual union operation could be order of n, at least in the at least that's what follows from the way we are arbitrarily deciding whose ID to change. So if we then multiply the number of union operations by the cost per union operation, or if we just follow this extreme case example, you'll see that the number of union operations in total will be given by the summation of a series which looks something like this, or you could more simplistically say that it's just order n times n-1, and so it's order n square. And so the total cost of union and find operations across this whole process would be order of n square plus m. And since m is always less than or equal to n times n-1 by 2, in other words, even if the graph is dense, this is going to be order n square, and if the graph is sparse, then m is order n, which still makes this order n square. So the total cost is now given by order n square, which if you compare to the previous solution we have, is not really an improvement. Let's assume that our graph in general is going to be a sparse graph, and we also had this quadratic complexity when we were running BFS or DFS all over again for each edge. So this method didn't lead to an improvement, but it's still going to be a stepping stone, and maybe we can now think of what the next step could be in order to improve the overall complexity. So if we had to give this method a name, what we could do is we could note the fact that the find operation was trivial here, so let's call this method quick find, because the union operation was expensive, but at least the find operation was quick.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today